So, today we will end this module with some practice problems, and I will just say a few things that in this module you have learnt about a technique for solving differential equations, which is called the power series method, and we have used it mainly to solve homogeneous second order differential equations. It is actually a fairly general method, and we will see some conditions in the next module how when you can use it and how you what are the modifications of the method you can do. Okay. But we have in this module we are mainly focused on trying to illustrate the use of the power series method. We solved the Legendre differential equation, we saw the what are called the polynomial solutions, and these occur very naturally when you are dealing with many problems. We saw something called an associated Legendre polynomial, which we used to describe the rotational states, the Hermite polynomials, which are used to describe the vibrational states. Okay. So, what I want to emphasize is that now the power series method, there are a lot of steps, you have to work out things, and finally you get various interesting relations. And what has happened is that there are a whole number of differential equations, okay, which are solved using the power series method, and these have been worked out in the past. So, people have worked them out. Okay. So, we have a very large number of these special polynomials. Okay. So, there is Legendre, we have already talked about Legendre, Hermite, okay, but there are many other polynomials. We'll look at some of those in the next module. Okay. So, let us work out a few practice problems. So, what I want to emphasize is there are two things to emphasize. One is how you use the power series method, and the second thing that I want to show is how you use properties of these say Hermite polynomials or spherical harmonics. Okay. So, let's go and let's start with the first practice problem, which is which essentially asks to use the power series. So, use power series method to solve y double prime plus 3 y prime plus 3y equal to 0. Okay. So, when I say solve, you mean this is a homogeneous second order differential equation. So, you can write the solution as a so get general solution okay, y is equal to C1 y1 plus C2 y2. So, a general solution has these two arbitrary constants C1 and C2. So, this is what you have to get from this by this method. Okay. So, let us go and start working out the method. So, if you want to solve this, then you will say you will start with the trial form. So, y is equal to sum over n equal to 0 to infinity a n x raised to n. Okay. And then after that, what you will say is that y prime is equal to sum over n equal to 0 to infinity a n n x raised to n minus 1, and y double prime equal to sum over n equal to 0 to infinity a n n minus 1 x raised to n minus 2. Okay. So, this is how you start the power series method. Okay. This is the first step in the power series method, is to write power series and write the derivatives. Okay. Then you substitute in this equation. Now, when you substitute in this equation, so the y double prime term will be as it is. So, I will write it sum over n equal to 0 to infinity a n n minus 1, and you have x raised to n minus 2. Okay. And then I can have plus sum over n equal to 0 to infinity 3. Now, x into y prime. So, I can write it as 3 a n n x raised to n with a plus sign. Okay. And then you have plus sum over n equal to 0 to infinity 3 a n x raised to n, that is for y, okay, equal to 0. Okay. Now, Now we can look at, if you want, you can look at x raised to 0 term. Okay, so if you look at terms of power x raised to 0, what you get is, in this case you cannot have any power of x raised to 0. In this case again you cannot have any power of x raised to 0. Okay. In this case you can have x raised to power 0. So what I want to say is, if you want x raised to 0 in the first term, you have to have n equal to 2. Okay. Now n equal to if n equal to 2, yes, okay. So in this case you can have n equal to 2. So what you will get is n equal to 2 into 1 is 2a2. Okay. In this case, if you have to have n equal to 0, but n equal to 0 term is 0. Okay. So you get plus 0. In this case n equal to 0, now you have 3an or a0, n equal to 0, so a0. So you have this equal to 0, or a2 equal to minus 3a0 by 2. Okay. Let us do x raised to 1 terms. Okay, so if you have x raised to 1, then n has to be 3. So 3 into 2 is 6. So you get 6 and a3 plus, now in this case you will get x raised to 1. Okay, so you get plus 3 into 1, so 3a1, and you get again 3a1 equal to 0. Okay. So or you will get a3 equal to minus a1. Okay. These are some of the relations you can do. Now you can ask, in general, x raised to n term. Okay, so what is the recursion relation for x raised to n? So if you want to have x raised to n, then what you should have is an plus 2, n plus 2, n plus 1. So you will have an plus 2, n plus 2, n plus 1 plus, now if you want to have x raised to n, then you have 3an n. So 3an n, and you have plus 3an equal to 0. Okay, or you can write a recursion relation now using this. You can write the recursion relation an plus 2 is equal to, now this is 3n plus 1, right, or n plus. So so what I can write this as, minus an, okay, and I have a 3 and I have n plus 1 divided by n plus 2, n plus 1. So I can write it as minus 3 an divided by n plus 2. This is my recursion relation. Okay, and you can, and incidentally you can just put, if you put n equal to 0, then you recover the a2 and a0 relation. If you put n equal to 1, you recover the a3 and a1 relation. Okay, so this is a general recursion relation from which you can get all the terms. Okay, so now that we have that, let's what we can say. Okay, so if you look at let's say you look at a4. Okay, so a4 you will say is equal to, so using this relation, a4 is minus 3 divided by now n equal to 2. So it is a2 into minus 3 divided by 4. Okay, and a2 is nothing but minus 3 by 2 a0. So it is minus 3 into minus 3 divided by 4 divided by 2 a0. Okay, so this is equal to minus 1 square 3 square divided by 4 into 2 A0. Okay. Similarly, I can write A6, okay, A6 as minus 3 by 6 A4, okay, and then if I use this relation, what I will get is minus 1 cube 3 cube divided by 6 4 2 A0. Okay. So, in general you can write A2n, okay, as minus 1 raised to n 3 raised to n divided by, so now I can write, I can factor the 2 here. So if I look at this, I'll just write it in a slightly different way, 3 cube divided by, now I'll take I'll take 2 cube into 3 factorial. So I have 1 into 2 into 3 into 2 into 2 into 2, so 2 cube into 3 factorial. So I can write this as 2 raised to n factorial. Okay, so this times A0. So I can write my A2n in this form. Very elegant expression. Okay. Now let's go, what happens when let's look at the odd polynomials. So what is, we already saw A3 and A1, now let's look at A5. So A5 equal to minus 3 divided by 5, A3 equal to minus 3 divided by 5 into minus 3 divided by 3 A1. So instead of minus 1, I wrote it explicitly this way, and again the reason will be clear. So this is minus 1 into square and 3 square divided by 5 into 3, 5 into 3, and I will just put a 1 also, just okay. Similarly, I can write A7 as, I can write by the same, what I will get is minus 1 cube 3 cube divided by 7 5 3 1. Okay. So you can write the general expression A of 2n plus 1 is equal to minus 1 raised to n 3 raised to n divided by, now what I have is 1 3 5 7. So what you have is 2n plus 1, 2n minus 1, 2n minus 3, all the way up to 5 3 1. So it is this product. Okay. So this is the expression for a 2n plus 1. Sometimes this is called a double factorial. This is sometimes you use the symbol double factorial for this. So sometimes this denominator is conveniently denoted as 2n plus 1 double factorial. Okay. So that is just a notation for this. Okay. So basically now we have our general solution. Okay. So we can write our general solution in this form. So y is equal to you have A0, okay, times, okay, what you have is sum over x raised to 2n, okay, and what you have is n equal to 0 to infinity, and what was the coefficient of x raised to 2n? What we saw, what was that, minus 1 raised to n, 3 raised to n divided by 2n, 2 raised to n, n factorial, okay, and you have the other term which is A1 times sum over n equal to 0 to infinity. Now I have x raised to 2n plus 1 minus 1 raised to n, 3 raised to n divided by 2n plus 1 double factorial. Okay. So this is my general solution, and you can easily verify that each of these will actually satisfy the solution. So each of the terms, each of these terms and this term will individually satisfy the differential equation. Okay. So in this way the power series has given the general solution. So this is the general solution, and this completes this problem. Okay. Now the second problem that I want to do, okay, this is a very simple, very nice illustration of using the recursion relations. So what you are asked to do is to calculate integral e to the minus x square h3 of x h4 of x dx from minus infinity to plus infinity, where h is a Hermite polynomial. So h3 and h4 are Hermite polynomials, and you are asked to calculate this integral. Okay. Now what you know, okay, so we know integral minus infinity to plus infinity e to the minus x square hn of x hm of x dx is equal to 2 raised to n factorial root pi times delta n m. Okay, so if n is not equal to m, it is 0. If n is equal to m, then it is this number. Okay. So now how will you calculate this? So here you don't have just h3 into h4, you have h3 x h4. Okay. Now these actually such integrals appear when you are calculating the transition dipole moment for vibrational spectroscopy. Okay. And in fact the idea, the selection rules for vibrational spectroscopy come from calculations involving such integrals. Okay. So it's actually a very relevant integral that you worry about. Okay, that we worry about such integrals a lot. So this x comes from the dipole moment operator. Okay, and this is something that we see a lot in spectroscopy. Okay, so now how can you deal with x times h4? Okay, so here we use a relation. We use recursion relation. Okay, what is the recursion relation? Okay, I will write it in a slightly different form. I will write x times hn of x equal to n times hn minus 1 of x plus half hn plus 1 of x. Okay, so this recursion relation is what we will use, and notice that the right hand side has no x in front, it only has Hermite polynomial multiplied by some constants. Okay, it does not have x. So now once you use this in the in this integral, okay, then you can easily do the integral. So what we will say is that h4 x times h4 of x is equal to, now it will be 4 times h3 of x plus half times h5 of x. Okay. So what I did is I put n equal to 4 and I got this relation. Now I will take this and substitute there, and then use the orthogonality condition. So when you substitute in the expression, okay, what you will get is the following. I will do it right here. So you will get integral minus infinity to plus infinity, okay, e to the minus x square. Now what you have is you have h3 of x, okay, then you have 4 h3 of x plus half h5 of x dx. Okay. Now this has two terms. Okay, so this has two terms. So the first term is integral minus infinity to plus infinity e to the minus x square h3 of x times h3 of x dx. Okay, and this is multiplied by a factor of 4, and the second term is half integral e to the minus x square h3 of x h5 of x dx. Okay, so now you use the orthogonality relation. So from the orthogonality relation, the first term Okay, so here you have h3 into h3. So if you go back to the orthogonality relation hn hm, so here when n is equal to m, okay, then you will get only this part 2 raised to n factorial root pi, because delta I of nn is 1. So what I will get is, what I will get in this case, n equal to m equal to 3. So you have 2 raised to 3 into 3 factorial into root pi into 3 factorial into square root of pi, 2 raised to 3. And the second case, here n is not equal to m, so this equal to 0. Okay, so the second integral is just 0, the whole term, is just 0. Okay, so then all you get is this, and this is your answer. So this turns out to be how much? So you have 6 into 8, 48 into 4, 192 square root of pi. Okay, so what we started is with an integral that looked like this, okay, and you got a number, okay, out of this derivation. Okay, so you got a final expression, you evaluated this integral. Okay, in order to evaluate that, you had to use this this orthogonality relation. Okay, now this orthogonality relation, I expect you to remember this constant factor. Okay, so I expect you to remember the orthogonality relation and the constant factor. Similarly, it is also expected that you remember the recursion relation for Hermite polynomials, because this is a very important relation that appears in lot of spectroscopy. Okay, so what is important about this problem is the following, that suppose, see when you want to do selection rules for spectral transitions between states V and V prime. So you are going from a vibrational state V to a vibrational state V prime. Okay, then what appears in this selection transition is a quantity that looks like so actually you can write that the probability of transition under what is called the dipole selection rule. So this is proportional to something that involves an integral just like this. So you have e to the minus x square by 2, rather what I'll write it in a slightly different way. So what appears is something that looks like this. So you have psi v of x psi v prime of x dx. Okay, and if you remember the expression for psi v, you had exactly an integral factor. So you have e to the minus alpha x square by 2, okay, and you have another e to the minus alpha x square by 2. So psi v, I should put a complex conjugate here. So what you get is because you had we had the expression psi v of x as proportional to e to the minus alpha x square by 2 times some Hermite polynomial of v of square root of alpha x. That was the expression. So now when you substitute that, okay, you get 1 e to the minus alpha x square by 2 from the psi v star, 1 from psi v prime. So you get a e to the minus alpha x square. Okay, then you have h v of square root of alpha x, h x h v prime of square root of alpha x dx. Okay, and now you can see this is a really amazing relation. So basically if I multiply by square root of alpha, okay, and let us say I divide by square root of alpha. So if I multiply and divide by square root of alpha, this will look like integral minus alpha infinity to plus infinity e to the minus, I will write this as square root of alpha x the whole square, okay, h v of square root of alpha x square root of alpha x h v prime of square root of alpha x, and what I will write is d of square root of alpha x, okay, and I will just take a I just have a 1 by alpha square, okay, 1 by alpha rather 1 by alpha, okay, 1 by alpha I will absorb into the constant. So essentially what I will get is if I say square root of alpha x equal to y, then this is basically proportional to integral minus infinity to plus infinity e to the minus y square h v of y h v prime of y dy, okay. So what you get, okay, so this is equal to now if you use y h v as if you use the relation, the recursion relation, then this becomes essentially proportional to integral minus infinity to plus infinity e to the minus y square. Now what you will get is h v of y, and you will get a term that looks like h v plus 1 of y, okay, and there is a factor of 1 by 2, and you will get another term that looks like plus v times, then the other integral will have exactly the same, but you have e to the minus y square h v of y, and you have h or v prime plus 1, sorry, v prime minus 1 of y dy. Okay, what I did is I used the recursion relation to write this as a sum of two terms, one involving h of v plus 1 and the other involving h of v minus 1 or v prime minus 1, okay, and each of these, and there should be a dy, each of these integrals is 0, okay. So probability of transition, okay, so this equal to 0 unless v equal to v prime plus or minus 1. So either if v equal to v prime plus 1, then the first term is non-zero, if v equal to v prime minus 1, then the second term is non-zero, okay. So if v is not equal to v prime plus or minus 1, then this term goes to 0, okay, and this is actually the selection rule. So in a vibrational selection rule, okay, you learn that the difference between the two states that are involved in the transition should be plus or minus 1, okay, and here we have seen a very elegant way to arrive at that result, okay, starting from the Hermite polynomial, starting from when we, and just to remind you, we use two properties of the Hermite polynomial. We use the recursion relation, okay, so this recursion relation, and we use this orthogonality, okay. So with just these two relations you can easily derive the selection rule for vibrational spectral transitions, okay. So I will conclude module 7 here, okay. So in the next week we will do some more power series method, so a little more advanced power series method, which is called the Frobenius method, okay. Thank you.